slides. Today I'm back to the blackboard. Right, so I'm going to talk about the process of how a primordial black hole could form. And in order to do that, a very, very important concept is the horizon scale. So I've redrawn this plot. Apologies, it may be a bit small to see, but just so I can leave it up. I did show this before in the very first lecture. And the idea that the Hubble scale is 1 over h. So that's the physical Hubble scale. To go from physical to a co-moving scale, you have a factor of a. So the co-moving Hubble scale is 1 over ah. And this is an inverse length. And what's of importance, both during and after inflation, is whether, one of the important quantities is whether the mode you're looking at has a longer or shorter physical wavelength than the co-moving Hubble scale. Okay. So today's horizon scale is 1 over h0. It's really c divided by h0, the distance light can travel in a Hubble time, but we're setting c is equal to 1. Okay, so that's today's horizon scale. What happened to the co-moving Hubble scale was it decreased like a factor of 1 over a, because h is constant during inflation. This is where inflation ends. This is t end. Then after inflation ends, the Hubble parameter starts decreasing quite rapidly. It decreases faster than the scale factor increases. So overall, 1 over ah becomes increasing, and it increases like a factor of a during radiation domination, then like a factor of a to the half during matter domination, and then it's actually decreasing again today because we're in an epoch of dark energy or lambda domination. And so this is very important, and I've drawn it piecewise. Of course, that's not quite realistic, but it's good enough for our purposes. I should have said, so the x-axis is n, e-folding number, which is the logarithm of the scale factor. Okay, so when you have a mode, initially during inflation, it will be inside the horizon, meaning k will be large compared to ah. Remember, k is not a physical scale, it's the Fourier wave number. Okay, so it's the inverse of length, and specifically in cosmology, we nearly always look at co-moving scales. So k is 1 over the co-moving length. Okay, so once your length scale is large compared to the horizon, remember at some point during inflation, the scale will exit the horizon, unless that's really microscopic. Then there'll be an epoch when k is much less than ah, meaning the scale is superhorizon. And there's a point during inflation when it exits the Hubble scale, co-moving Hubble scale, when k equals ah, and then that's here for a large scale, or much later for a small scale. And then much later during inflation, after inflation has ended, when 1 over h is growing again, it will re-enter the horizon. And this is really, really important. It's this,
sorry, can I ask a question? Actually, that plot, it's for me, it's a little bit of unclear. For example, for the top horizontal line, yes, that's the present horizon, right?
Yes.
But the x-axis can present the time, right? I mean log a can represent the time flow, right?
That's right.
So what's the point? I mean, why do you compare that line with the present horizon lines? I mean, they are in different time, right?
So that co-moving scales are constants but the distance between two co-moving observers, so two observers are both moving with the expansion, is a conserved quantity. As long as you're talking about co-moving scale and not physical scales, because the physical scale is growing, of course, with the expansion. So this scale 1 over h naught, really, technically, I should have written 1 over a naught h naught. Okay, but a naught we set equals to 1, so the scale factor today is 1. And so this 1 over h naught has a constant co-moving scale. And there was a time when it was inside the horizon during inflation, then it left the horizon, and then it re-entered recently in quotation marks. Okay. And you're right, the x-axis, because there's a one-to-one relation between the scale factor and time, you could write this in terms of time here as well. But these are sort of straight diagonal diagonal lines when you make this the log of the scale factor. So this log A is not proportional to log T. Or for some epochs it is, but the relation does change.
But the 1 over AH it's a co-moving Hubble horizon. It's not a constant, right?
It's not a constant, no. But 1 over h naught a naught is a constant, because h naught is evaluated today, and so is a naught. So this thing here is a function of time or scale factor. This thing is a constant, because I'm evaluating it today and using that same value at any time in the past. It's just a constant co-moving scale. And this is a different constant co-moving scale down here. It's a much, much smaller scale. So it left the horizon during inflation much later, and it re-entered during radiation domination. And this, of course, the reason for drawing this much smaller scale is this is what we're thinking about, what primordial black holes might form. It's a much smaller scale. But again, these are co-moving scales. Okay. So the reason why I'm sort of stressing this is really because we'll see that the black hole mass is proportional to the horizon mass, and the horizon mass is given by k equals ah. That's not the mass, of course, but that gives you sort of the length scale, which gives you then or you can deduce a characteristic mass scale. Okay. So what's the significance of horizon entry? Well, 1 over h is the age of the universe, roughly. Universe. Not during inflation, but after inflation, this is true. During inflation, this is actually not a good estimate at all. So for example, during radiation domination, which is what we're interested in, and it's easy to deduce this from the Friedmann equation, A goes like t to the half. So this implies h, which is equivalent to a dot over a. So it's very easy to put in. The constant of proportionality doesn't matter. This is 1 over 2t. Okay. So the age is, t is 1 over 2h. This is really the age, and you can see this is up to a factor of 2, 1 over h. So that's why 1 over h gives you the age of the universe, or a good estimate. And in fact, there's a nice little exercise to put in today's value. I won't do it, but h naught is 70 kilometers per second per megaparsec. So you put in that a megaparsec is about 10 to the 19 kilometers. Okay. Then you can estimate what this is in terms of seconds. It's something like 10 to the minus 18 seconds. And then notice the units really are time. And then you take the inverse of that and you get about an age of 10 to the 18 seconds, which is about 10 billion years. And that's in sort of units we understand. So 1 over h naught really is the age of the universe. Then if you multiply that by c, you get the, roughly speaking, the observable horizon scale of the universe. And in units where c is equal to 1, 1 over h naught is both the age and the horizon scale of the universe. So we've got Hubble distance. This board's not quite as good, right? This is c over h, but in our units, this is 1 over h. This is distance light can travel. In time. Yes, in which time? Well, it's in a Hubble time, in time 1 over h. It's simply the speed divided by the time. Sorry, the speed times time is the distance you can travel. Of course. So, 1 over h is approximately the causality scale. Now in units where c equals 1, at the time of the age of the universe, when h has this value, so at the time 1 over h. And I appreciate that it might be clearer, if I sometimes inserted c. On the other hand, writing all of these equations, when you insert c, life becomes quite messy quite quickly. So again, a co-moving scale. Remember, k was the inverse of the co-moving scale, so this thing is 1 over k. This is 1 over ah. And hence, k equals ah, right, is the horizon scale. This was 1 over h. But this is physical scale. Okay. So you have to divide it by a to get the co-moving scale. So once again, k equals ah, very important, implies horizon entry or exit. Specifically, I haven't written it, but you might want to add in your notes, this is the co-moving horizon scale. By the way, the notes were uploaded to the website this morning, so if you want to just annotate notes directly, you can find them there in LaTeX. The notes from yesterday is a copy of the slides. Okay. So the reason to go into all of this, perhaps slightly painful detail about the horizon scale is that primordial black hole formation is a causal process. How quickly can collapse happen? Well, collapse can only happen when an overdensity can communicate the fact that it's overdense. So when a perturbation is outside the horizon, there's no way for any information to travel across the scale of that perturbation and get gravity to act and start collapsing. So causality implies the collapse will not begin until no collapse while k is less than ah. Because that means, remember, small k is large scale. It means the relevant length scale is still outside the horizon.
Can I add something about this? So, okay, this makes intuitive sense, but for example, we saw that during slow roll or ultra slow roll inflation, that super horizon perturbations could grow, and I can kind of picture this as correlations between, you know, the two different sides of the Hubble sphere. And so in that case, this intuition doesn't hold, so I don't really understand it.
Yep, it's a very good point. So the growth of the superhorizon modes, which can happen both with isocurvature perturbations, so when you have more than one field, or with ultra-slow roll, it feels like it breaks causality. It actually doesn't, because basically the initial conditions are set up to make those perturbations change in a coherent way across superhorizon scales, but they're not communicating with each other anymore. It's like you can prearrange, you know, if you synchronize your clocks, that you'll both do something at exactly the same time.
Yeah, okay.
That looks like you're breaking causality, but you're not really.
Yeah, okay, I see.
So perturbations, yes, they can evolve in superhorizon scale. That's a very good question, and it is counterintuitive. But that won't allow things to actually move a greater distance in the horizon scale. So nonetheless, even if they had sort of pre-coordinated what to do, they wouldn't be able to collapse by moving our horizon distance.
Yeah, okay, clear.
Yeah, that's a good point, and honestly, I've confused myself about that point many times. So it is tricky. Okay. So we'll go with this. It is true. Yes, it's not trivial at all. But I am just trying to give intuition, you know, not the actual details. So the horizon scale really is the key concept. Okay. And we'll find there's a one-to-one relation, well, an approximate, not exact, but approx one-to-one relation between the primordial black hole mass, which is going to be set by the horizon mass. Basically, it's going to be a very large overdensity. So once it re-enters the horizon, causality allows gravity to basically tell the opposite sides to collapse. And most of the matter inside that horizon, which is mainly radiation, assuming a radiation-dominated universe, will fall inward and collapse. So MPBH will be approximately MH, which is a function of K. You can also write it as, well, MH is a function of time, because when I write K, I really mean K equals AH. So, you know, how do I know which time to use? Well, it's the time when the relevant scale has the value K equals AH. Of course, then there's a one-to-one relation as well between time and scale factor, so I can also write it as MH as a function of scale. And we're going to assume, once again, for the rest of this lecture, we're going to assume that primordial black hole formation is during radiation domination. It's not a requirement.
Why is this approximately equal, the mass of the primordial black hole to the horizon mass?
Yeah, I'm not going to really show that, but intuitively, when you've got a very large overdensity, and I'll quantify just how large it has to be, the whole thing's going to collapse quite quickly within about a few Hubble times. And because the overdensity is so large, it will drag in nearly everything inside the horizon. I mean, that's basically what defines the relevant length scale, which is sufficiently overdense to form a black hole. So if it was only a small fraction, you'd really be looking at the wrong length scale. You should look at a smaller length scale, where the overdensity is larger for that given scale.
Oh, I see, yes. Thank you, yes.
Mm-hmm. Yeah, this is very, very different from galaxy formation. Galaxy formation takes billions of years. It takes literally millions of Hubble times. And the galaxy which forms is completely disconnected from the horizon scale by the time it's formed. Because this is much faster, the horizon scale is still relevant at the time of formation. So we're going to assume radiation domination. And there are interesting alternatives. We spoke about that. Pippa also spoke about this yesterday during the office hour. It may actually be easier when the pressure is smaller, as we'll see in a second. I'm going to assume radiation domination for the rest of this lecture for the formation. Because we know before matter domination, there was a radiation dominated epoch. We know it continued to early times before Big Bang nucleosynthesis, and possibly long before that. So the horizon mass at radiation matter equality, when we know we switch from radiation to matter, is huge. It's 10 to the 16 solar masses. So we're really interested in times long before matter radiation equality, further to the left, when the physical scale is smaller, when the co-moving scale is smaller, and when the horizon mass is smaller than that. Okay. So we've got a very large pressure. It implies large pressure, which is omega rho, which is a third of rho. Okay. So in order for gravitational collapse to beat this very strong pressure, we're going to need a very large density perturbation. By large, I mean large amplitude perturbation. So if we compare to the CMB scales, and I just want to make clear, this is the special initial conditions. The reason why we don't generically expect primordial black holes is that when we think about, again, on CMB scales, delta rho over rho, which we're going to call rho, this thing goes like the square root of the power spectrum. Roughly speaking, the power spectrum of the curvature perturbation. I showed this in lecture 1. There are some constants in between, but we don't need to worry about this. So what was the amplitude of this on CMB scales? It was the amplitude AS, observed by the Planck satellite. This is, well, AS is 2 times 10 to the minus 9, take the square root. This is 5 times 10 to the minus 5. So this was CMB scale. This is really tiny. If a gravitational density, over density, is of order 10 to the minus 4, say, then it's going to take a very long time for collapse to happen, but the radiation pressure, in fact, is going to win. We need something much, much larger. And I'll be a bit more precise, but it requires delta rho over rho close to order unity to beat the large pressure, which is comparable but not quite as large as the energy density. So we can already see, if the power spectrum is close to scale invariant, so if slow roll for all inflation, for the whole duration of inflation, then this implies, again, I mean, there was a bit of discussion once with Nicola, exactly what you mean by slow roll, but the standard sort of slow roll, meaning slow roll parameters of order 10 to the minus 2, would really imply 0 primordial black holes. So that's why we study ultra slow roll inflation during lecture 2. It's to see a concrete mechanism whereby the amplitude of the perturbations can become large on superhorizon scales. It doesn't really matter if they become large on subhorizon or superhorizon. What does matter, though, is that they are large, that delta rho over rho becomes large when you re-enter the horizon. Okay. So once again, this is really saying primordial black holes they require special initial conditions. Okay, I see, but not new physics. Or at the very least, not a new particle. You can debate whether the non-standard inflaton potential is new physics or not, but of course inflation itself is new physics. But for this lecture, we can actually, for the most part, be agnostic about what caused the perturbations to become large. We're simply going to ask, well, how large do they have to be at horizon entry at this time, and whether they were generated by inflation or by something else doesn't really matter. So, if you're a fan of the cyclic universe or string gas cosmology or whatever else, it doesn't matter. We're simply asking what the initial conditions need to be once the co-moving Hubble scale is growing during radiation domination. So, this, to my mind, this is the most special thing about primordial black holes as a dark matter candidate, the fact that they're not a new particle. Again, I'm not saying that's better or worse, I'm just saying it's quite obviously different. Okay, so we want to now estimate, delta rho over rho of order unity. That's a bit too crude. Let's think a little bit more about that. So that we want to estimate delta C, where this is the collapse threshold. Okay. This is the collapse threshold measured at horizon re-entry. And this was first estimated by Bernard Carr while he was Stephen Hawking's student back in 1975. This was only a few years after the very first papers about primordial black holes. So in fact, the idea of primordial black holes predates the idea of inflation. Again, sort of showing that you don't need to study it in the context of inflation. It's just today, most people think that's the most likely source of the initial conditions. And he used a sort of Jeans length type of argument where you estimate, well, the length scale, you compare that to horizon scale, you also compare that to the time it would take a pressure perturbation to travel from the center of your overdensity to the edge of the overdensity. And he assumed spherical symmetry. And, I certainly won't try to go into that argument. I found delta, which we'll define as delta rho over rho, needs to be greater than some delta critical. Okay. The question is, what is this value of delta critical? And he found this should be equal to the sound speed squared. And this is at, everything is at k equals ah. So at horizon entry. And this was in fact quite a rough estimate because he used Newtonian gravity. And it's very difficult to do this using general relativity, as you might imagine. So let me just define this. So Cs is the sound speed. It's the sound speed of the perturbations. And the slower the sound speed, the longer it will take a pressure perturbation, which is generated by the collapse, to travel outwards, and hence the more time gravity has to make the thing collapse. So a smaller sound speed corresponds to a lower pressure, which you may know from thermodynamics, which corresponds to easier collapse. So in radiation, Cs squared is equal to the equation of state parameter, which is a third. So that would imply delta critical. Yes, it's order unity, but it's not exactly 1, it's actually a bit, it's not quite as bad as that, it's a third. So the speed of gravitational attraction is 1 in units where c is equal to 1. So the pressure perturbations, it's a third, or 1 over the square root of 3, and hence it leads to this estimate. Now, GR simulations have in the meantime been done by several groups, although until very recently all of the simulations assumed spherical symmetry, so there were basically 1 plus 1 dimension, time plus the radial coordinate only. And recently, though, even some 3-dimensional simulations have been done, and they have found, and if you think about it, we're studying something with a horizon, we're studying both a cosmological horizon and a Schwarzschild horizon. So you might think that the Newtonian gravity approximation would be very wrong, but it's actually not, it's not bad at all. They found delta critical is about 0.45. And this is independent of the mass of the primordial black hole. It just depends on the equation of state, so assuming radiation domination. And intuitively, I don't think that's such a surprise, because it's like a self-similar process. The horizon scale is the only relevant length scale, the horizon time, the Hubble time is the only relevant time scale. So as long as the relative amplitude of the perturbation is the same, it will collapse in exactly the same way, taking exactly the same length of time if you measure time in units of the Hubble time. So this is independent of mass. There is, though, one caveat, which, the car estimate's pretty good. It does break down, though, when the sound speed goes towards 0. It would then predict everything collapses in an early matter-dominated epoch, and that's, of course, not true. And where it goes wrong is that when you're talking about small initial perturbations, then they take a long time to collapse, and then non-spherical effects become important, and yeah, you'd have to completely redo this. But for rare large amplitude perturbations, which is the only thing of interest in early and radiation domination for primordial black hole formation, that estimate's pretty good. Okay. So as I said, just don't try to use that estimate in the limit that the sound speed is going to 0. So what do we want? Well, we'd like to know how large the amplitude of the perturbations now needs to be in order to generate some interesting number, non-negligible number of parts in the universe where delta is greater than delta critical. So we want to estimate this such that we get some primordial black holes, but not that we get so many that it's ruled out. And to be a bit more precise, interesting normally means that there's a non-negligible fraction of the dark matter in primordial black holes. And I introduced this yesterday in the slides. So we've got, let me define, F PBH and rho PBH. Oh, sorry. No, that's wrong. I have a rho dark matter measured today, time T0. So this was defined yesterday, but I'll write it down again. It's a very important thing. And so, of course, right, FPBH equals 1 would imply all dark matter are primordial black holes. And if you're not assuming a monochromatic mass, then you really have to, this rho PBH is, of course, the total energy density of all primordial black holes. Okay, so we're going to want to know which values of the power spectrum generate FPBH to be example 1 or 10 to the minus 2 or even 10 to the minus 10, but not 0 and not bigger than 1, because bigger than 1 would be ruled out because then you've overproduced the dark matter. Now the problem, a challenge is this is evaluated today, but we really want to know how this corresponds to the fraction of the universe which could collapse to form a primordial black hole at the time of formation, which is during radiation domination. So again, in radiation domination, we've got rho totes. It's proportional to rho radiation, proportional to e to the minus 4. While after the primordial black holes form, we know rho PBH is proportional to e to the minus 3. Okay. So very simply, this of course means that, rho PBH over rho total is proportional to A. So this energy density fraction is growing proportional to A from the time of formation until the time of radiation matter equality. So let's estimate these, how this fraction changes. So let's go in rho PBH. At the time of equality, so radiation matter equality. Well, this fraction doesn't really change between equality and today. It changes a bit, but only by factors of order unity. And for these lectures, it's much better I give you intuition than precise numbers, so I'm going to drop factors of order unity. So this is approximately equal to the fraction today. It's certainly not true by more accurate than a factor of 2. I don't care about factors of 2, so this thing is FPBH. And then this factor has grown from the time of formation by a factor of A until matter radiation equality. So this thing, I've written equal, it's really twiddles, so approximately equal. This is A equality over A formation times the fraction at the initial or formation time, which we call beta. Well, I'll define beta as soon as I create a bit of space.
Sorry, can I ask a quick question?
Sure. Yes, please.
So, FPBH is the density of PBHs over the density of dark matter total. And okay, and in the first part of the equation, that's the whole density of the universe.
Correct. Yeah, I shouldn't have written equal, sorry. But the dark matter is an order 1 fraction of the universe today.
Okay, okay.
And it's also an order 1 fraction of the universe at the time of matter radiation equality.
Okay, thank you. Yeah.
But order 1, that's the key, yeah.
Okay.
Within a factor of 2-ish. But yes, in fact, you could replace this, rho total at matter radiation equality is almost exactly half. is in dark matter. So I could have written here rho dark matter as well, and it would be equally good or bad. Let's say equally good up to a factor of 2 or 3. So I'm just going to define, so beta is the fraction of primordial black hole to the total, and here this is important, this is the total, not dark matter at the time of formation. So we're going to do calculations about how a power spectrum amplitude generates the collapse into primordial black holes. That will be done at the time of formation. And then we need to remember that we've got this scaling by this factor of A from the time when formed until the time of matter radiation equality. Typically, this factor is much, much bigger than 1. It can easily be a billion or bigger. And this is not unusual. This is standard for any dark matter formation mechanism, that you only need a very, very small percentage of the universe to be in the form of dark matter at the time dark matter forms, and it then becomes relatively more important, like the scale factor A, until matter radiation equality. So I'm now going to make another approximation. This whole lecture is full of approximations, which is that primordial black hole formation is nearly instantaneous. And that one's actually quite a reasonable approximation. It's fast. By fast, what do I mean? It takes a few Hubble times so a few times 1 over h, which in terms of e-folding is about 1 e-fold. In fact, during radiation domination, you can check that 1 e-fold of expansion, so the scale factor growing by a factor of 2.7, corresponds to about 9 Hubble times. And why is that useful? Well, it means I can treat, when I'm talking about here a formation, I can treat the formation time as being equal to the time of horizon entry. So we treat PDH formation is when k equals AH. So again, when the relevant mode, the relevant length scale, where you've got a peak in your power spectrum, is equal to AH. That's both when the mode enters the horizon and when the mode collapses. And at this level of accuracy, that's absolutely a good approximation. I think I'll go a little bit further and then we'll stop for a break in perhaps 5–10 minutes. Okay, but are there any questions about this? Are you happy to accept that, this is a reasonable thing to do? It will simplify things a lot. And why is it fast? It's because delta rho over rho is so huge. Delta rho over rho at horizon entry, not later, but at horizon entry, is of order 0.45. But it's bigger than that in order to collapse to a black hole. Galaxies take billions of years because delta rho over rho at horizon entry is 10 to the minus 4. So it's a very small overdensity and it has to take a long, long time to collapse. Okay, so we're now going to try and estimate the horizon mass, which I've already told you is approximately the PBH mass, so MH. because again, because we've got such a huge overdensity, pretty much everything is dragged on that scale into the black hole. And the density of the black hole itself is roughly the same as the density of the background universe was at the time when that scale entered the horizon. However, it wasn't a black hole at that time because it was still co-moving outwards with the expansion. So we want to estimate the horizon mass. So that's a fun little calculation. It doesn't take too long. So what's the horizon mass? Well, it's the density times the volume. Treat it as a sphere, so using spherical symmetry, which is a good but not precise approximation. So, I'm probably sticking too many numerical factors given the other approximations, but so for the volume of a sphere, both ends pi, rho. Now we need the radius and the cube of the radius, of course. Right, 4/3 pi r cubed and times density. Now the radius we want going to choose is the Hubble scale, but we're not going to use co-moving radius because we want, this is the mass. Mass we always think about physical mass. So although I'm normally talking about co-moving length scales 1/AH, so much so that I often get this wrong myself, that I made a clear note in my notes to here we have to use physical radius. So we don't use 1/AH. To get the physical scale, we have to multiply that A by A. So to be, in a sense, really paranoid, multiply by A over AH, and cube it. Okay. So 1/H is the physical length scale. Now, so what can we do with this? So this thing, I'm now going to drop these numerical factors. I was being a bit too precise anyway. So this thing is proportional to rho h to the minus 3. Now, how does h to the minus 3 depend on rho? Well, I can look at my Friedmann equation and remember that the universe is spatially flat very quickly during inflation. So I drop this, so h squared is proportional to rho. So this whole thing is proportional to rho to the minus 1/2. Okay, so this is proportional to 1 over square root of rho. How does rho vary with scale factor? Well, we know during radiation domination, the energy density decreases like a to the 4, a to the minus 4. So this thing is proportional to a squared. And a goes like, let me write this clearly, a goes like t to the 1/2, so a squared goes like t. Since this is important, let me just rewrite. So we've got, or we used rather, h squared proportional to rho, proportional a to the minus 4, and a is proportional to t to the 1/2. And yeah, this is all correct. Now I have dropped numerical factors. It's a pain to carry them around, but it's perfectly feasible if you normalize this, for example, to the mass at matter radiation equality. So let me just write this down with the numerical factors, explain it briefly, and then we'll take a break. So I'm not going to justify the numerical factors. I'll just tell you you can go away and check them if you've got perhaps an hour or so to spare. And so this thing is, okay, so the mass is proportional to a squared. So it depends on a at the time of formation. Let me write that as, over a equality, right, it's going to be proportional to the square of this quantity times the mass of radiation matter equality. This thing, M equality, is about 10 to the 16 solar masses. That's an order of magnitude. So we can immediately see something like a solar mass black hole, right, is going to form when scale factor was a tiny, tiny fraction of the scale factor of matter radiation equality. And you can rewrite this in terms of mass and time as being approximately 10 to the 15 grams T over 23 seconds. Okay. And this thing is proportional, linearly proportional to time. But you might be puzzled that, you know, the mass is proportional to the radius cubed, so why wasn't it proportional to a cubed? And the answer is because the density is decreasing while the scale factor is growing. And you're sensitive to the density at the time of formation. And the last thing I'll say for the break is, why is it often written in this form in many review articles, the relation between the mass and the time is written like this? Well, it's because this is the mass of a black hole which would be evaporating today. So through Hawking evaporation, if your primordial black hole initial mass is less than 10 to the 15 grams, it's evaporated by today. If it's of the order of this mass, you could see the Hawking radiation today. If it's much heavier, then the mass is essentially completely constant today, and it will be for a long, long time into the future. So we see a mass of black hole which evaporates today formed 10 to the minus 23 seconds after the Big Bang, so very, very early. And everything I've done, if you're thinking about masses lighter than this, then of course what I've done so far is true for the horizon mass, which is true for the initial primordial black hole mass. It's not true for the black hole mass today because it's evaporated. And I think this is a good time to give us a break. Are there any questions though before we take a break?
May I ask?
Mm-hmm.
So, are there good reasons to not consider the PBH formation during the matter era? Is it because they lead to bigger masses, or?
If you're thinking about the late time matter era, then yes. Well, there are two things. One is exactly right. The masses are greater than 10 to the 16 solar mass. And the other thing is that's actually quite a large scale, and on those sorts of large scales, there are other constraints telling us that the primordial power spectrum wasn't large enough to allow delta over rho to be a border unity.
I see.
Much smaller. However, an early matter-dominated epoch is possible. It's just we don't know whether that happened or not.
Before the radiation era. Okay.
Yeah, exactly.
Okay, thank you.
Mm-hmm.
I also have a question. I can see that the primordial black hole mass scales with time. So, for example, a supermassive black hole would form at a later time. Is it possible to incorporate such a production with the respecting the constraints of CMB?
Very good question. It's respecting the standard CMB constraints, meaning what the Planck satellites observed on scales larger than about a megaparsec. Yes, there's no problem. However, and I'll talk about this a little bit tomorrow, when you think about the mu distortions of the CMB, so the deviation from a perfect black body temperature spectrum, then there are problems. Because they probe smaller scales than the standard CMB, but nonetheless, not very small scales, but on the other hand, supermassive black holes. So if you're thinking like 10 to the 6 or so solar masses, that's physically not such a small scale. And again, there are other constraints. But I'll show you that tomorrow. I promise to show you that. I'll at least briefly mention that again tomorrow.
I also have a question.
Mm-hmm.
So I'm a bit confused about the the values of the density contrasts you spoke about, because I know, for example, in the spherical collapse model, where you think of some overdensity collapsing on the matter-dominated background, I think the value for the density threshold is 1.6. So it's much higher than the values you spoke about, but you said that for galaxies it's 10 to the minus 4. So I'm wondering if I mix something up, or what's the fundamental difference in the setup?
Right, yeah, good point. There are many definitions of what this initial density is. So I'm speaking about the density relative to the total density, not the matter density, and evaluated at the time of horizon entry. And it's at the time of horizon entry, because after that time it will grow. And I mean, if you look at the density contrast of the galaxy today compared to the background, it's much, much bigger than order unity. But nonetheless, that's not the initial value at horizon entry. And that's the value which needs to be huge. And for galaxies, they really form on the scales we observe from CMB, well, at least galaxy clusters do. They form really where delta rho over rho was tiny. So that 1 point, what did he say, 1.9 or 1.7, that argument is calculating a different definition of delta rho over rho.
Okay, and also at a different respect time, right? Reference time.
Yes, absolutely.
Okay. Okay, thanks.
Yeah.
May I ask a question? We said that primordial black holes are a convenient dark matter candidate because it requires some special initial conditions and not a new physics. I just wanted to ask, what is the matter which are these black holes are made of matter, or they are pure space-time curvature?
They're made mainly out of radiation, in fact. They're made out of whatever the background universe is made out of at the time when they form, because they are made out of a physical collapse of whatever the stuff is in the background. And at very early times, like 10 to the minus 23 seconds after the Big Bang, we don't really know what that form of radiation is.
So these kind of black holes are different from astrophysical black holes in the matter.
No, they are formed out of different stuff. That's for sure. The late black holes today are formed out of baryons.
Yes.
Almost exclusively. However, once a black hole has formed, it has no hair, the so-called no-hair theorem.
Yes.
Once the black hole formed, unfortunately, you can't directly know anything about how it formed. You have to deduce it indirectly. So, for example, like I talked yesterday about the Chandrasekhar mass as being sort of the mass where you need to, well, it's the minimum mass you can form a compact object in astrophysics with baryons. That doesn't apply at all to primordial black holes. But yeah, they're made out of different stuff, but unfortunately we can't probe what's inside. Well, certainly not without dying. So.
Okay, so we can treat them as the same objects, but in principle it is not said that they are made of the same kind of matter.
Correct.
Okay.
Yeah. In fact, they're almost certainly not made, because this is probably long before baryogenesis. We don't know for sure, but there are probably no baryons yet in existence.
Okay, thank you.
Good. Oh, but these are good questions. Okay, I think we should take a 5-minute break. Yeah.
Okay, very good, Chris.
Come back at 20 past.
Yeah.
Yep, and I'll try and finish it.
Thank you.
Cool.
Yeah.
Cheers. Great. So yeah, it was a short break. Tomorrow I'll be a bit more relaxed, but There are certain things I need to show today so that people can do the tutorial problem this afternoon with Curvature. Okay, so I've given you these relations. Just going to give a few more. Also in terms of their co-moving wave number. Okay, so we've got, remember K equals AH, horizon entry. So A is proportional to T to the half, H is proportional to 1 over T, 1 over T to the half, proportional to 1 over A. Okay, so that means the horizon mass is proportional to A squared, which is K to the minus 2. And roughly speaking, when you substitute in the values, this is 10 to the 13 solar mass times K to the minus 2 in units of megaparsec squared. Okay. So the units of K are inverse megaparsec. So now we've got another important relation. We had one in terms of time, one in terms of scale factor. Here we've got one in terms of K. And so let me just, yeah, this one here. So this is 10 to the 16 solar mass. So just to give an example then, for MPBH is solar mass, we need beta. Well, it's the inverse of 10 to the minus 16, the square root of that, so you find the beta needs to be avoided 10 to the minus 8. Okay. And sorry, I should have said this is assuming would imply FPBH is equal to 1. Okay. Based on the fact that the solar mass horizon entry time is about 10 to the minus 8 of the matter radiation equality scale. So it's just giving one example. Now, if you look at even lighter primordial black holes, they form even earlier, so that growth by the factor of A is even larger, then you can talk about even smaller values of beta. Okay. So now I want to talk about how do we estimate beta? And the easiest way is using something called Press-Schechter theory. I hope some of you have seen this before. If not, I'm afraid I'll just tell you what it says rather than why or how. Press and Schechter formalism, which is to estimate the collapse fraction of the universe into primordial black holes. And according to this formalism, beta, for some, which is a function of the mass, and remember this was the density in primordial black hole divided by the total formation. Okay, that estimates this to be the same as the fraction of sort of subvolumes of the universe where the density contrast is greater than the critical threshold. So you have to integrate, and this now P is not the power spectrum, this is the PDF, the probability density function of delta with respect to delta. And clearly this is not going to be precise. But given that the density of the primordial black holes at the time they form is not very much larger than the density of the background universe, it is larger, but by a factor of an order of magnitude, not many orders of magnitude. Then in every subvolume where delta was large enough on the relevant scale, it will collapse to form a black hole. It's going to be a very rare process. And everywhere else where delta is less than delta critical, you don't get a black hole, you're just left with radiation, whatever the radiation is made of at that time. And I'm going to do something a little bit wrong, but again, you know, everything's a bit hand-wavy at this level. I'm going to talk about this in terms of the curvature perturbation, estimator in terms of curvature perturbation. Again, the PDF of our dr. So I'm using R is approximately delta, evaluated at k equals AH. And again at k equals AH. Away from the horizon, this relation can be completely wrong. It also depends on your gauge. This is in co-moving gauge, but I just don't have time to go into gauge issues. Okay. And once again, this is not the power spectrum, this is the PDF, the probability distribution function. And we're going to assume for simplicity Gaussian perturbations, which again, the density contrast cannot be precisely Gaussian, it's a non-linearly related to R, but at a reasonable approximation, these can be said to be roughly equal and both to be Gaussian. So we're going to assume Gaussian. For both delta and for R, and then the variance of the Gaussian perturbations is set by the power spectrum amplitude. Okay. So this is the power spectrum, this is the PDF. Please, when I type them, this is the straight P, this is curly P, or calligraphic P. Okay. I hope it's clear, they're not the same thing. Now, technically, this is not absolutely correct. The density contrast is some smoothed function of the curvature perturbation. You should put in some window function. You should have a smoothing scale, which is the scale of primordial black hole formation. The answer is going to depend on which window function you use to smooth the perturbations. And it also depends on the fact that this relation is not quite correct. Also the fact that even if the curvature perturbation is Gaussian, delta, there's some nonlinear correction, which means the density contrast is not quite Gaussian. But you know, I'm trying to cover inflation and primordial black holes in a week, so we're going to run with these approximations, and they will give you correct orders of magnitude. So they'll give you good estimates and a lot more intuition than me just giving full, very complicated equations.
Excuse me, Professor.
Mm-hmm.
It's not clear to me this argument for which we can approximate the density contrast with the comoving curvature perturbation. They are related via a non-local way, right? One is the Laplacian of the other. So why we can approximate them?
Yes, you're absolutely right. They're related through the Laplacian. The Laplacian gives you basically a k-squared factor. It's a second derivative. So in first place, that's a k squared. Now, however, it's k over ah squared. So when k is equal to ah, then that factor is order unity.
I see.
But only then. So this really has to be evaluated specifically at horizon entry. And then the difference is order unity. Once you're a factor of 10 away from horizon entry, the difference is a factor of 100. And this becomes a terrible approximation.
Okay, I see. Thanks.
But you're absolutely right. One is really the derivative of the other, and it's, you know, I'm skipping through a lot, but in order to get some concrete numbers, which will be correct, but I won't have really justified why they are correct. So, good question. You're right. there's a little bit more detail in the notes, and of course I reference, papers where this is done much more rigorously. Okay, but now I'm gonna run with this. I'm gonna use a Gaussian probability distribution function. And so what we can do is you can use the asymptotic expansion. Okay, and because we're interested in beta being much less than 1, if you put it in the Gaussian, if you do it, you're integrating very deep into the tail, where you've got this exponential sensitivity. This thing is a half times the complementary error function, so error function complementary. This is relatively standard notation. It's a function of delta critical, which is where you're integrating from. Then you put square root of 2 times the standard deviation of the perturbations. And again, we're going to approximate the perturbations as being the square root of the power spectrum amplitude at horizon entry. Okay. And well, sorry, this is actually exact, but we can now use the asymptotic expansion. Now this thing is approximately sigma over square root of 2 pi delta critical and this is true in the limit that beta is much, much less than 1, which is equivalent to saying that this argument here is greater than 1. So sigma squared should be much less than delta critical squared, or sigma. And that's exactly the regime we want to be in, because we don't want to overproduce primordial black holes, so they've got to be very rare at the time of formation, even if they're all of the dark matter today. So this is a very important result, this thing. As I say, it's not entirely accurate, but it gives the right intuition. You really are exponentially sensitive to the amplitude of the perturbations. Now, observational constraints are normally made in terms of FPBH, the fraction of dark matter today. You can then convert it, if you know the mass that you're constraining, into a constraint on beta, which will be a much smaller number than the value of FPBH. And so we can then use the value of beta to constrain the allowed value of the power spectrum amplitude. So, I'm going to do something very rough, very crude. Not wrong for intuition, but be cautious. Let me take then the log of beta of both sides. So, the logarithm of both sides. So log beta is minus log 1 over beta. This thing is minus over 2 sigma squared. I've dropped all of this, okay? I'm being that crude. Even though this factor is not very close to 1, this factor is much smaller, much further away from 1 than this factor. So I've just neglected all of this. Again, not very right, but not terribly wrong. So if I then plug things in, just rearrange this, so this means P of R, approximately sigma squared is log of beta. Then if we put in delta critical is 0.45, take the square, that's pretty accurately 0.2. Log. Okay. So again, this won't win any prizes for accuracy, but it does help build intuition to use these crude estimates. So basically, when you fiddle around with delta critical, or the amplitude of the power spectrum, you have an exponential sensitivity in beta. So, if someone does a new numerical simulation and says delta critical is 0.47 instead of 0.45, and they phrase the difference in terms of beta, the difference looks exponentially large. However, if you phrase the difference in terms of the required amplitude of the power spectrum to generate some given value of beta based on observational constraints, then the change is very small. It just changes like the square of delta critical. And that's an important message. You know, we've got exponential sensitivity for beta, but not for the amplitude. It depends what you want to do, which one is more important. But of course, authors like to phrase the importance of any new work they do in terms of beta because their difference becomes exponentially large. And very often, though, that's really quite misleading and not important. Okay, so let me, build up some intuition by saying, so if FPVH is equal to 1, and for solar mass black holes, by the way, this is really observationally excluded. It can't be bigger than about 10 to the minus 2, but, let's just think about what amplitude of the power spectrum would we need to get all of the dark matter in solar mass primordial black holes. I've already shown you this would imply beta to the order 10 to the minus 8. Okay, based on the fact that the matter radiation inequality mass is 10 to the 16, so the inverse of this squared. Well, in that case, the power spectrum amplitude required is of order 0.2 divided by log, 1 over 10 to the 8. Which is 0.011. So here finally we've got an estimate. It's of order 10 to the minus 2. Okay. So the power spectrum needs to grow from 10 to the minus 9 on CMB scales right up to 10 to the minus 2 on the relevant scale for primordial black hole formation, at least for the solar mass. So we're now starting to see, and this is the right order of magnitude. A more detailed calculation changes the number a bit, but by a factor of a few, not by an order of magnitude. Now you might ask, okay, that was for solar mass, what about a different mass? For example, the best constraint on beta it's from MPBH evaporating today, of order 10 to the 15 grams, plus 15 of course, grams, because these would be evaporating today that have a very bright signature in gamma rays from the Hawking evaporation. And this is really quite incredible. On this scale we've got beta, also they form much earlier. So the amount of growth of the scale factor from when a 10 to the 15 gram black hole would form until matter radiation equality is a very, very large increase. Okay. So the constraint is that beta is less than about 10 to the minus 28. Remember, this is a dimensionless quantity. So instead of 10 to the minus 8, we've got 10 to the minus 28. Now, naively, intuitively, you'd think, well, if my observational constraint on beta has improved by 20 orders of magnitude, surely the constraint on the power spectrum amplitude will have improved by a lot. Not 20 orders of magnitude, but surely also a lot. And that's simply not the case. Okay. Because for this case, we need now PR. To generate them with this value of beta would imply PR, it's of order 0.2 divided by log of 10 to the 28. So this is 28 log 10, the other one was 8 log 10. So the difference is a factor of 8 over 28 only. So this thing is 0.003. So this is of order 10 to the minus 3, but actually a bit bigger. And the difference in PR to form all primordial black holes of solar mass, or a very small subset of dark matter, all dark matter in solar mass primordial black holes versus a very, very small fraction of the dark matter in today decaying primordial black holes, well, the difference in PR is it's a factor of 28 over 8, which is equal to 3.5. So, that's the power of this exponential sensitivity. And no matter which mass we're talking about, if we're in radiation domination, and if the perturbations are Gaussian, then sort of need PR between 10 to the minus 3 to 10 to the minus 2. Larger than 10 to the minus 2 will always be excluded. Smaller than 10 to the minus 3 will be so small that you'll get basically 0 or even precisely 0 primordial black holes inside the entire observable universe. I want to stress though that there are two important caveats, and the fact that I did such quite crude approximations isn't the problem. That's really not the problem. What is, to some extent, the problem is that, this was assuming Gaussian perturbations, which, if the perturbations are non-Gaussian, because we're studying an event, a very rare event deep in the tail, even a not very large amplitude of non-Gaussian entity can have an exponentially large effect. So assuming Gaussian, and we were assuming radiation domination, and that's we talked about yesterday in the office hour. So some were listening. The perturbations can be dramatically smaller, exponentially smaller, if you had an only dominant matter-dominated epoch. So if before the inflaton had finished decaying into radiation or something else meant that you had a very early matter era, you could have potentially a much, much smaller amplitude and still an interesting number of primordial black holes. But this is, I think this is an important thing nonetheless. Within these assumptions, there's only a very restricted range which will generate any primordial black holes and which won't generate too many. And this is related very directly to the second tutorial problem, which is also online already. So if we ask, how sensitive are these answers to, for example, delta critical? Well, guess what? I can make the answer look important or unimportant depending on what I decide to do. So if I decide to compare values of beta, so if I choose sigma squared of 3 times 10 to the minus 3, remember this corresponded to a very small value of beta of 10 to the minus 28. Now let me compare what the values would be. So beta of delta critical equals a third, divided by beta of so this, remember this was exponentially sensitive. There is a prefactor, but most of the difference comes in the exponential. So this will be e to the minus delta critical, which is now a third squared. I'm choosing a third because that was Byrnes Carr's original estimate for delta critical. Over 2 sigma squared, divided by using today's modern value, using full GR numerical simulations, and e to the minus 0.45 again over 2 sigma squared. So plug in this value of sigma, we'll get this thing is different by 6 orders of magnitude. Okay. So it looks like the change in the value of delta critical is so enormous that it's, super important and it's crazy, not to lose sleep over this value, the difference or the uncertainty in the value of delta critical. Okay, so that sounds, this is big. However, clearly I can instead take the logarithm of everything and phrase the difference in terms of which value of sigma do I need to get the same value of beta. So in that case, I just take the difference. So if I want to give it, to get a given value of beta, instead, how do I need to change the amplitude of the power spectrum? Well, then we've got sigma squared of delta critical is a third, divided by sigma squared of critical is 0.45. Remember, these power spectrum or standard or variance values are proportional to delta critical squared. So this thing is third squared which is almost exactly a half. So now the difference doesn't look so important. Again, you can exponentiate things. Beta is always exponentially sensitive to what goes on in your calculation. You get a big change. On the other hand, you can take the logarithm and ask which value of the power spectrum amplitude do I need to get a given value of beta, and then you're only logarithmically sensitive to changes in beta, and you're only sort of linearly or quadratically sensitive to changes in delta critical. Right up here. So here's the power spectrum amplitude in terms of beta. If I fix beta, I'm only sensitive to the value of delta critical. So I'm not exponentially sensitive. Okay, so we're close to finished. I'm going to tell you one time, which I already showed yesterday, which is something close to my research interest, which is the effect of the Qcd transition. So an exception to, when you should probably phrase things in terms of the difference of the power spectrum amplitude is the Qcd transition. So I showed this in slides. The Qcd transition, it's not a sharp phase transition. The pressure doesn't drop dramatically, but nonetheless, when the quarks are bound into hadrons, the pressure drops by a little bit. And so omega drops down to 0.25. Okay, so the equation of state drops by about 25%. From the standard radiation dominated value of a third. And when does it do it? Well, just by pure coincidence, if you look at the energy scale of the Qcd transition, it's about 200 MeV, at least for the most important part where the equation of state drops by the largest amount. The horizon mass is equal to the solar mass. Which really is a nice coincidence. Now this drop in the equation of state means that primordial black hole formation will become easier, and delta critical drops down to 0.4. So this is what, about a 10% drop. 0.45. Okay. So that doesn't sound very much, does it? A 10% reduction, but remember, when we changed it to a third, the Byrnes-Carr value, you got an increase in the primordial black hole fraction by 6 orders of magnitude. So what happens here? Well, this reduction corresponds to beta being enhanced by 10 to either 2 or 3 orders of magnitude. So again, relative to the fact where you had no transition, where omega was just equal to a third. And this transition is part of the standard model of physics. It's not sort of new physics being thrown in. So this means if the power spectrum is much amplified on the relevant scales for LIGO-Virgo, so if power spectrum of R is of order 10 to the minus 2, on, let me call it LIGO-Virgo mass scales, by which I mean when the horizon mass is between, say, 10 and 50 or so solar masses, if it stayed roughly scale invariant down to the solar mass, then you're going to get 2 or 3 orders of magnitude more production of primordial black holes with the solar mass. Okay, so we'll overproduce them relative to the standard calculation where delta critical is a constant. So if this is true, and for sure we don't know if it's true, I did show in quite a bit of detail yesterday the slides where we found evidence that certainly not all of the compact objects they're observing are primordial black holes, but they could be a subdominant contribution. Then we expect then you'll get a big enhancement of solar mass. Okay. Big enhancement, again, meaning 2 to 3 orders of magnitude. And these are below the Chandrasekhar mass. So this is a potential smoking gun signature. I mean, but in quotation marks, a potential proof of primordial black holes, if seen. And LIGO-Virgo, although this is very light for them, it's a small mass, it's difficult to see. It is within their sensitivity if the distance of a merger wasn't too far away. And, this could be seen, in principle, with existing technology. So again, with LIGO-Virgo. And this is ongoing. There are new ones, Kagura's just, I think, come online recently in Japan. LIGO India's to come, they're all being upgraded. So I'll finish on this positive note that, there is a motivation and there is a possibility to see a black hole and to know that it didn't form in the standard way, it didn't form out of baryons, it's not a dead star. And tomorrow I'll talk a bit more about the observational side, both about current constraints and potential future signatures to finish. But for today, I think that's enough. There is a tutorial this afternoon led by Pippa, so it's already online. I encourage everyone to please, I know you've got a very busy schedule in this workshop, but try and download it and have a look at it at least, if you can beforehand.
May I ask a question? So beta, it's really a function of k, right? Like the k at horizon entry, essentially.
Yes.
So if you want to calculate the fraction of f, let's say, you have to integrate over all k, right? Of this function.
Yes.
Okay, I see.
Yeah. Now, if your power spectrum is narrowly peaked, they'll all be nearly the same mass, and that's not a very important step. But if you have quite a broad peak, then yes, it's crucial to integrate over all masses. And I haven't been doing that. I've just been assuming basically a monochromatic mass.
Yeah. Yes.
Yeah.
Can I ask something?
Yep.
So I saw that when you wrote the variance of perturbation, sigma squared, you said it's proportional to the primordial amplitude.
Mhm.
So this means we are essentially neglecting any transfer function, right?
Correct. And with the function.
Is this because it's horizon crossing, or is it?
Yes,
Okay.
exactly right. It's not exactly correct, but that's exactly the correct reason why I'm making that approximation, and that's why it's a reasonable approximation. Yeah.
Okay, just wanted to make sure. Okay,
Yeah.
thank you.
Yeah, no, it's very important. Nearly everything I've written is at k equals AH. And as someone also asked before, right, there's a Laplacian between them, so you've actually got a factor of k squared, but it's k over AH squared, so when k is equal to AH, these approximations are reasonable, but only then.
I see.
Excuse me, I have another question.
Mhm.
So we have perturbations above the critical threshold, and then we have perturbations at the level of 10 to the minus 4 that lead to galaxies. And what about things in between? Like, are they washed away by diffusion damping?
Very good question. It depends on the scales and it depends on the other physics. Maybe I could quickly just sketch what's going on. Well, what might be going on. So we've got, as you correctly said, on CMB scales, the perturbation is 10 to the minus 9, up to about the inverse megaparsec. And so there's a P of R. Then on some scale, we need this to reach about 10 to the minus 2, maybe 10 to the minus 3. And this is forming PBHs. And somehow we need to grow between them. Now, if the growth is quite close to the left, I'll show this tomorrow, you could get spectral distortions of the cosmic microwave background. In between, there's some range of scales where if the power spectrums of order 10 to the minus 5-ish, you could get what are called, I'm deliberately drawing this vague, but up to probably about the parsec scale. And so what's that then? 10 to the 6-ish inverse megaparsec. You could get something called an ultra-compact mini-halo, which would be assuming most of the dark matter are not in primordial black holes. You could get a memory of the large amplitude perturbations here from dark matter being clustered, but on very small scales. So the radiation won't retain any memory of the initial perturbations because of the pressure, but if the dark matter has already formed, and if your power spectrum grew something like this, then there might be some hidden signature in the dark matter, which might be possible to see in the future with some sort of lensing survey. Or if dark matter annihilates, then you would expect a much boosted annihilation signal from the small scale inhomogeneities.
Okay, I see. Thank you.
Yeah, and it would be great to find more ways to probe the small scales in general. There's primordial black holes. I'll talk about two others, primordial gravitational waves and mu distortions. So mu distortions are roughly around here, and then pulsar-timing array is somewhere around the 1 solar mass scale. For most of these scales, we just have a constraint of about 10 to the minus 2 from primordial black holes and nothing else. So we need more.
Yeah, okay.
I also have a question.
Mm-hmm.
If you drive the projector theory further, you should be able to get also a mass function for the primordial black holes, right?
Mm-hmm.
Did you do that, or did you consider doing that because you could observe then the abundance of primordial black holes with this mass function?
Yes, yeah, I've been involved in doing that, and other people have as well. I think the original might be Niemeyer and Jadomzik back from something like 1999. There's been various things we added on top, like the effect of the Qcd transition, but yes, we have made mass functions, and generically you get something close to a log normal mass function.
Oh, okay.
So you get if your power spectrum at least is relatively narrow, you get also a relatively narrow mass function, but with a tail to both sides. Yeah, but absolutely right. I mean, we use that as an ingredient when we were comparing primordial black holes to astrophysical black holes for the LIGO Virgo events. So we had to assume a mass function, and there is a motivation for the sort of mass functions we assumed.
Okay, yeah, that's interesting. Thanks.
Yeah, no, it's a good idea.
Okay. If there are no other questions, I think we can. Are there other questions?
Yes, one question.
Okay, please.
It's about the threshold. The argument by Carr is a genius argument, you're right. There was been an upgrade by Arad, I think, where there is a calculation of the threshold that is gauge dependent, right?
It is gauge dependent, yes.
And this is not a problem in some sense.
Well, it's a problem if you use the wrong gauge, or if somebody calculates the threshold in one gauge, but you calculate the curvature perturbation in if you calculate the density contrast in a different gauge. So I've skipped over all these details. I've written the curvature perturbation curly R and goes like delta.
Yeah.
That's only approximately true in the co-moving gauge for delta. So what I've been using implicitly was the co-moving gauge for delta.
Okay, but also the simulation, namely the 0.45, by Musco is gauge dependent simulation.
Yes, that's right. I mean, they choose a gauge to do a simulation,
yes.
But that value of 0.45 is comparing to the same gauge.
Yes, because in Arada gave also an expression for his calculation to be connected with the Musco one, a sort of its paper is delta tilde, that is a sort of rewriting of its formula to be comparable with the numerical calculation, and so it is a gauge dependent one. Okay.
Mm-hmm.
And there is a way to calculate in a theoretical way the threshold in a gauge independent way. Like the margin potential for the.
Yeah. Honestly, I'm not sure. When you do numerics, you have to choose a gauge. Analytically, what I'm aware of, people have also chosen a gauge. But in principle, it must be possible to just use gauge invariant variables like we do during inflation. But whether the calculation has been done in that way, I'm not sure. But as long as you do the calculation in a gauge and you know how to transform your results to another gauge, it doesn't matter that you did a gauge-dependent calculation. As long as you're able to translate your results correctly between gauges, right, you should get the same answer as if you'd started with the gauge invariant calculation.
Yeah, okay.
So I think everything is fine.
Oh, because in my mind there is sound or something wrong, because the threshold should be physical quantities maybe, and like the power spectrum of inflation that is calculated in a gauge invariant way. So, namely, you can start with some gauge, but the final answer is gauge independent. So in this case, I expecting something like this.
Yeah, I'm sure that's possible. Whether that's really been done explicitly, I'm honestly not sure. The picture I've sketched, of course, is quite approximate. This is also very high level, right? This is way beyond the first course in primordial black holes. People really use the compaction function.
Yeah.
And, you know, they don't actually simulate delta directly. At least many people don't. And likewise, I think since in recent times, people have used more complicated variables. But none of them are useful for our intuition, so I don't think they're important at this level.
Okay.
Yeah.
Thank you.
You're welcome.
Okay. So I think we can stop here. Thanks a lot, Chris.